Okay, we shall go through the proof of Egorop's theorem. Again, the idea is whenever there is convergence, the convergence is nearly uniform. That is, a convergent sequence of functions is nearly uniformly convergent. The crucial word is this nearly. I mean, that's vague. But the theorem, of course, is precise, tells you to what extent this can be done. So we're in a locally compact Hausdorff topological space. Mu is a regular measure on the Borel sigma field, and start with a set of finite measure. Take a sequence of measurable functions so that fk goes to f almost everywhere on E. Now then, given epsilon positive, there is a closed subset A of E. Often this can be made compact. And for example, if you are in Rn and X is Rn and E, the set of finite measure is actually bounded, then this closed subset of E will actually be compact. So given a closed subset in Rn can only be non-compact by being unbounded. If you can ensure boundedness, then it's compact. Given epsilon positive, there exists a closed subset A of E, such that the difference in measure of E and A is less than epsilon. I mean, mu of E minus A is less than epsilon, and Fk on A Fk goes to F uniformly. So one produces a closed subset which is very close in measure to the measure of E, such that the convergence is uniform. All right. So given a convergent sequence, so this is what the word nearly means, that almost on the whole set E, it's uniformly convergent, not exactly on the whole set E, except on a subset of small measure. That smallness can be determined by U. That is, you take E and epsilon, and except on a subset of measure less than epsilon, it's uniformly convergent. Okay. Because the proof was as follows. I'm going through it again because this was towards the end, and this is an important, complicated proof. So assume Fk, not assume, I mean Fk goes to, what is given is Fk goes to F almost everywhere on E. And well, this almost everywhere means that there is a null set on which you don't know what happens. It doesn't go, it doesn't converge. Throw away that null set from E, nothing changes. You are still on a set of measurable set of finite measure. Measurability doesn't change. The property that the measure is finite doesn't change. So, and then you have the advantage that it goes everywhere. So Fk goes to F everywhere on E. After throwing out the null set and replacing, so if the null set is N, then replacing E minus N by E, we assume without loss of generality that Fk goes to F Fx. Okay, now consider these sets E and K, which are subsets of E, such that mod Fjx minus Fx less than 1 by n for all j greater than k. Okay, so the n determines the level of precision. It's 1 by n, and k is for all j greater than k. All right. Now, clearly, this is an increasing sequence of sets. Why? Well, look at En1. Now, this means mod. I mean, if you fix n, then in k it's increasing. En1 is all x in E, such that mod Fjx minus Fx is less than 1 by n for all j greater than 1. So then certainly that satisfied for all j greater than 2. So En1 is contained in En2. the same argument why E n k is contained in E n k plus 1. Okay. And why does E n k converge to E as k goes to infinity? That means the union over k equal to 1 to infinity, union k equal to 1 to infinity E n k is E. Well, they're all contained in E, so the union is contained in E. And could it fall below E? Well, take some x in the union, so that x is in some E n k, which means take an x in E. I want to show that the union is equal to E. The union is contained in E. Take some x in E. Now what you know is fkx converges to fx. Just a sequence of complex numbers. Fkx is a sequence of numbers, it converges to the number f. That means there exists a large enough k such that the difference between fkx and fx becomes less than 1 by n for all j greater than, there is a large enough k such that mod fjx minus fx is less than 1 by n for all j greater than k. That's the meaning of convergence. And so you know that x belongs to that E n k. Okay. This depends on x, of course. This k depends on x. So the union is E. So E n k increases to E as k goes to infinity. So mu E is the increasing limit of the mu E n k's as k goes to infinity. So consequently, you will have, since so far n is fixed, only k is going to infinity. Okay. Since these numbers mu E n k, they increase to mu E, so there will be a large k. To remember the dependence on n, I call it kn. Large kn such that mu of E minus E n k is less than 1 by 2 to the power. Because mu E n k is converging to mu E. These numbers are converging there. Okay. And the E n k are all contained in E. So the difference mu E minus mu E n k is really the measure of the set, mu measure of the set E minus E n k. That's what is really going to 0. Okay.
Okay, sir.
Now choose capital N so that summation n equal to capital N to infinity to the power minus n is less than epsilon by 2. It has to, some such capital N has to be there because this is the tail of a convergent series. All right. Set A tilde equal to intersection n greater than equal to n, small n greater than equal to capital N. What is capital N? Capital N is the one obtained from this line, the red underlined line. And set A tilde equal to small n greater than equal to that capital N, E n k n. Okay. Why? We'll see. Okay. Now these E n k's are all contained in E. So this intersection, of course, is contained in E, and mu E minus A tilde is what? So A tilde is this intersection. So when you take complement of the intersection in E, what you get a union, right? So that union, and then of course, if you have a union, then the property of measure is less than equal to summation n equal to capital N to infinity mu of E minus E n k n. E minus E n k n, and then if you take the union over all small n greater than equal to capital N, is precisely E minus A tilde. Okay. Now, what is mu of E minus E n k n? That is less than 1 by 2 to the power n. And consequently, this sum is less than epsilon by 2, because it's starting from some epsilon by 2 to the power capital N, then it becomes 2 to the power capital N plus 1, etc. is certainly less than epsilon by 2. Okay. So note that now, what have we found so far? By all this jugglery, we have now found a measurable subset A tilde of E such that mu of E minus A tilde is really small. That's all we have done so far. We haven't been able to say anything about the behavior of the functions or how the sequence converges, sequence Fj converges on A tilde. That we haven't said that yet. Now we shall. So is everything clear so far? I need to know that before I proceed to the next step.
Sir, I have one doubt.
Yeah.
So, sir, E minus A tilde leaves finitely many E and K's now.
A tilde is an intersection of infinitely many E and.
Oh, okay, sorry. Good.
A tilde by, you have the definition of A tilde here.
Right, sir. Fine.
Anything else?
No, sir.
Okay. All right. So starting with again, let's recall, starting with a set E of finite measure and a sequence of functions which converges pointwise on E. I have so far done nothing much. I've just found an A tilde, a subset, a measurable subset. Not even a closed subset that we aim to find. And a measurable subset A tilde, which is very close in measure to E. Why have we found this A tilde? Here is the reason. So now, okay. Remember, A tilde is a certain intersection. A tilde, definition of A tilde here. It's an intersection. If you take a point, so let's see how the sequence behaves on A tilde. That's the aim. If you take a point x in A tilde, because it's in the intersection, it's in every E n k n for n small n greater than or equal to capital. If point x is in E n k n, what happens? What happens is here in this line. For x in E n k n, I just put a tick mark here. That tells you what happens when x is in E n k n. All right. Now, given a delta, I would choose a large n such that 1 by n is less than delta. So then if x is in E n k n, because mod fj minus fx is less than 1 by n whenever j greater than kn, I'll have mod fj minus fx is less than delta whenever j is greater than kn. Let's first note that. That's what happens if x is in E n k n. Then mod fj minus fx is less than 1 by n, and I have chosen n large enough so that 1 by n is less than delta. So mod fjx minus fx is less than delta whenever j greater than kn. So what is the final upshot from here all the way up to here? The final upshot is that if x is in A tilde, okay, given a delta positive and x is there, suppose delta is positive, then given x in A tilde, just a minute. X is in ENKN for all n greater than or equal to n. And so, well,
by the Archimedean property, there exists some kn such that 1 by 2 to the kn less than delta, and then f of jx minus fx less than 1 by 2 to the kn.
okay. Okay. I guess what needs to be done here is a little change. Just give me a second. Okay, to be completely correct, perhaps as follows. Choose N1 here. Choose N2 here, and then so then for x in A tilde, both things will be satisfied. That x mod fj minus fx is less than 1 by little n, which is less than 1 by capital N, because little n is greater than or equal to capital N. And yeah. So what is the upshot? The upshot is, given x in A tilde, I have been able to find a number which is this k, such that mod fjx minus fx is less than delta whenever j is I guess just k sub k capital N will do. Yes, give me a second. Oh, okay. Things are really very simple. Sorry about that. Sorry about this confusion. Right. Okay. Okay. Sorry about this confusion in the middle. I have gotten certain A tilde. It's a measurable subset such that E minus A tilde has a small measure, just this much so far. Now take an X in A tilde. I want to show, my aim is to show that Fj converges uniformly to F on A tilde. So what do I have to show for that? I have to show that given a delta, I can find a large number such that whenever j is greater than that large number, mod Fjx minus Fx is less than delta for all x in A tilde. Now for any x in A tilde, x belongs to ENKN for all n greater than equal to capital N by definition of A tilde. Now this means that mod Fjx minus Fx is less than 1 by n. Now less than 1 by n will mean it's less than delta. So whenever j is greater than kn, then mod Fjx minus Fx is less than delta. So Fj Sushil, can you help me a bit? Sushil?
Yes, sir.
Yeah, can you check this argument later, and in case it requires a modification, please write it and send it to me so that we can give it to the students.
Sure, sir.
Yeah, just this uniform convergence part on A tilde. Okay, now A tilde is measurable and Fj converges uniformly on A tilde. I hope this argument is correct here. I am not 100% sure, so I requested Sushil to take care of this if necessary. This is possible, maybe that's an epsilon by 2. This is possible by regularity. This is why I needed E to be a regular measure. So you can approximate a measurable set from inside by closed sets. So mu of E minus A now less than equal to mu of E minus A tilde plus mu of A tilde minus A. This is less than epsilon by 2, and that's less than epsilon by 2. Altogether, it's less than epsilon. So we have uniform convergence on A tilde, the part of the proof which I'm not completely sure of, which I requested Sushil to take care of. But other than that, note that what we did is we produced a measurable subset A tilde such that mu of E minus A tilde is less than epsilon. And then we can approximate this measurable subset by a closed subset in measure by regularity of the measure. That is mu of, I can find a closed subset A so that mu of A tilde minus A is less than epsilon by 2. So altogether mu of A minus A will be less than epsilon. And if we have uniform convergence on A tilde, then we will have uniform convergence on a subset. So we have produced a closed subset A on which the sequence converges uniformly. That's Egorop's theorem. The moral is that every convergent sequence is nearly uniformly convergent in the following sense. So let's go back to the statement of the theorem once more to see what can be achieved. So Fk was a sequence of measurable functions which converges pointwise on a subset of finite measure. Then, given epsilon positive, a closed subset of this measurable set can be found such that the difference of measure between A and A is only less than epsilon, and Fk converges uniformly on this closed subset. Okay. So with that, so that's the first thing, that all convergent sequence of functions are nearly uniformly convergent. So these statements are, I think, due to Littlewood, who said this. Okay. The second thing is a measurable function is nearly a continuous function. Now that's a very strong statement. That's what Lusin's theorem is. So it says, let f be a measurable function let E be a set of finite measures. So again, we are in a locally complex topological space with the Borel sigma field and a regular Borel measure on that. So for example, Rn with the Borel sigma field and the Lebesgue measure will do. Let E be a set of finite measure. Let okay. When I say a measurable function, I automatically mean a real or complex value. That is, I'm not allowing the value infinity. In measure theory, they do sometimes, but in these theorems, this is not allowed. Given epsilon positive, there is a closed set F with F contained in E. Again, F depends on epsilon. Again, a very remarkable statement that given epsilon positive, there is a closed subset F with differences in measure being less than epsilon, such that on this closed subset, the restriction of F is continuous. So this F bar and then capital F below means we are restricting the function f to the closed subset f. There it's continuous. Understand the theorem carefully, because a closed subset is a strange thing. We don't really usually talk of continuity on closed sets, but this is the best that can be achieved. That's what happens here. In particular, a closed subset, for example, if it doesn't have a limit point, then continuity there becomes trivial. Okay, and such trivial situations do arise. But in many cases, it's nice. The closed subset is nice. Okay. We first prove the theorem. When f is a simple function. A simple function is a measurable function. I mean, that's the simplest kind of measurable functions. A simple function means you can partition the whole set into finitely many partitions. On each partition, the function is constant. Okay, now, since the measure is regular, get closed sets f1 up to fn such that fi contained in ei and mu of ei minus fi is less than maybe epsilon by n. E1, E2, En are measurable sets, so I can approximate them from inside by closed sets in measure. Let f be this, then mu e minus f is what? Well, E is this disjoint union of E1, E2, En. Fi's are contained in Ei. So E minus f is simply the disjoint union of Ei minus Fi. And that's equal to summation I equal to 1 to n mu Ei minus Fi. Each is less than epsilon by n, so the whole thing is less than epsilon. So f is a closed subset because f is a finite union of closed sets. So closed subset of E such that mu of E minus f is less than epsilon. Consider f restricted to this f. Now look at this. So when you restrict f to f, what is it? I mean, you take an x in f, that x belongs to one of the closed sets fi, and there fi is contained in ei. So this is equal to ai if X belongs to Fi. It's automatically continuous. There is nothing to prove really. I mean, how do you prove that something is continuous? So you take, for example, a sequence xn going to a point x, for example. X is inside a closed set. So, okay, this. I mean, we are in a locally
each
compact
set Fi, F is F restricted over F is a constant function. So
that
we
is right.
can say this.
Right. Okay. So it's a constant function, but how are you using the closeness of the set capital Fi? That's what is important. I mean, on EI also F was constant. That's what you need to think. It's just that if X is in Fi, then there is a neighborhood around X which is
Yes.
disjoint from all other Fj. That's
Content
local
in
compact.
fully Fi.
Contained in fully Fi. Yes. That's local compactness. That's why. And this might not be true for EI. Okay. That's exactly the argument. Okay, so that's for simple functions. Now get a sequence of simple functions Fn going to F pointwise, which you can always do, which we did last time, the actual construction. That is, given a measurable function F, you can always construct a sequence of simple functions converging to F pointwise. We did this last time. Okay. So each Fn is a simple function. Now apply what we already proved. We already proved the theorem for simple functions, so we can use that. Fn's are defined on whole of E. E is the set of finite measure on which we started with, on which F is a measurable function defined. Okay, so Fn, since Fn is a simple function, so by what we have already proved, I can get a closed subset capital F. Now, since everything depends on n now, so it's capital Fn, so that mu of E minus Fn is as small as we want. I've chosen it to be epsilon by 2 to the power n plus 1. And little fn restricted to capital Fn is continuous. This is exactly what we proved in this paragraph, which is on the screen now. Okay. Okay. Apply Egorop's theorem. How shall we apply Egorop's theorem? Egorop's theorem tells you that a pointwise convergent function sequence is nearly uniformly convergent. That's what we shall do. So by Egorop's theorem, and this is where mu E finite is used. Egorop's theorem was for sets of finite measure. There is a closed subset F naught contained in E such that Fn converges to F uniformly on F naught. Now, as you can see, we are kind of in good shape. Given a measurable function F on this set of finite measure E, I have first found a sequence of simple functions approximating F pointwise. That's number one. Because Fn's are simple, I can apply what I have already proved. Namely, I have already proved that there is a closed set Fn contained in E, such that E minus Fn has very small measure. So there is a little bit only outside Fn contained in E, and little Fn restricted to capital Fn is continuous. That's number one. Number two, I have found another set which I call capital F naught, whose measure is also very close to the measure of E, on which the convergence is uniform. So if I now throw out the portion that is outside F naught, outside F1, outside F2, etc., altogether they will probably make a set of only small measure, and after I throw out, I shall have uniform convergence. That, and on F naught, okay, let's see. I'll have uniform convergence and I want to retain continuity. So this is my final closed set now. Arbitrary intersection of closed sets is closed. Fn's are all closed. So this F is closed. Note that F is contained in F naught. So on F, I have uniform convergence, because on F naught, I have uniform convergence and F is contained in F naught. Are the sequence of functions little Fn, are they continuous on F? Well, F is contained in Fn, capital Fn, and little Fn restricted to capital Fn is continuous. So on a subset, it's continuous. So everything is done now. That is this. So altogether, this is less than. Altogether, the set of the measure E minus F is less than epsilon. The set F is closed. Each Fn is continuous on F. F contained in, because F is contained in Fn. And Fn goes to F uniformly. Uniformly on F. This is because F is contained in F naught. So we are done. Uniform limit of continuous functions is continuous. Okay, again, Lusin's theorem states that if F is a measurable function on the Borel sigma field of a locally compact topological space, and E is a set of finite measure, then given epsilon positive, you can find a closed subset, capital F of E, such that mu of E minus F is less than epsilon, and F, which is defined everywhere, F restricted to capital F restricted to capital F is continuous. Okay. I'm not saying it can be continuously extended to whole of X. That's a stronger statement, and at the moment I'm not saying anything like that. How shall we do this? Okay, we shall somehow produce a closed set F which is very close to the set E in measure, and we shall realize F as a uniform limit of a sequence of continuous functions on F. Uniform limit of continuous functions is continuous. That is how the function F will be made to be continuous. Okay, we first proved it for a simple function. Simple function means that you partition the set X into several parts. On each part, the function is a constant. What can stop the function from being continuous? What can stop is the following, that these EIs are of course disjoint, but EI closures might intersect. Obviously, right? I mean, you take let's say the interval 0, 1, and your E1 is an interval from 0 to open half. E2 is the interval open half to 1. Now you set the step function which is 0 on the first half, 1 on the second half. Now there is a problem about continuity. Agreed? Simply because the issue is that E1 closure and E2 closure intersect. And then you can come from E1 and you can come from E2 and you will get different limits. This is the problem. That means the only thing we have to do is somehow we have to separate the parts on which the function little f is constant. If you can separate them, then if the closures cannot intersect, then if there is a gap between the closures, then we are done. Agreed? Okay. So this is where the regularity of the measure is used. Get a closed subset capital Fi of EI such that mu of EI minus Fi is very small, epsilon by n. Take F to be the union of this. So F is basically, so you have divided X into several parts, E1, E2, etc. In E1, there is an F1. In E2, there is an F2. In E3, there is an F3, like that. Remember the interval example that I just gave. There, this becomes very simple. Okay, but it's the same idea. And so if I put capital F to be the union, then on each component of capital F, the function little f is constant, and the capital F's the capital Fi's are separated. Okay, that's what makes the function continuous. For the general case, take a sequence of simple functions pointwise. So the convergence is only pointwise. The way the sequence of simple functions is constructed, it's only pointwise. But then we shall apply Egorop's theorem, of course. We apply Egorop's theorem, get a subset, closed subset F0, such that mu of E minus F0 is less than epsilon by 2, and on F0 the convergence is uniform. Fine. But that's uniform convergence. Fine. But what use is the uniform convergence if the functions are not continuous? I won't be able to say that the limit is continuous. So to make the functions continuous, apply what we already just proved. So get a closed subset capital Fn of E, such that Fn is again very close to E in measure, and little fn restricted to capital Fn is continuous. Now it's very simple. Take F to be the intersection of all the Fn's. Capital F to be the intersection of all. Now, E minus F, although you have taken intersection, nevertheless, E minus F is still very small.
Sir,
Yeah.
hello, sir.
Yeah.
Sir, how can we say that this F is contained in F0?
Which F?
So this intersection of all fns.
Because set takes n equal to 0 to infinity.
Yeah. This
Sir,
F, right?
But F0 we get is independent, that we get from Egorop theorem.
F0 is contained in E.
Yes, sir.
Yes.
So later you argue that this F is contained in F0. So therefore, there is a uniform convergence as well continuity both.
That is right. Your question is why this F is contained in F0?
Yes, sir.
Is intersection of A and B contained in A or not?
Yes, sir.
So now look at the definition of F.
Oh, sorry. Okay, fine.
Okay. So mu of E minus F is less than epsilon. I mean, straightforward countable additivity of measure. The set F is of course closed because it's intersection of closed sets. You can take as many closed sets as you want and intersect them. It means closed. Each function is continuous on F. Each Fn is continuous on F. Why? Because capital F is contained in capital Fn and little fn is continuous on capital F. Okay. So every little fn is continuous on whole of capital F. And as Sumit Kumar just pointed out, Fn goes to F uniformly on capital F because capital F is contained in F0 and on F0 the convergence is uniform. Now uniform limit of continuous functions is continuous, so that's why. Okay, maybe we stop here. There are 4 minutes or so. Remember there is a class tomorrow. Satya, what exactly is the time for tomorrow's class?
Sir, it is the same time, sir. It is same time. Sorry, sir, 1 minute.
It's
It
not
is
same time.
4:45 to 5:45.
4:45. Yeah. Okay.
Yes.
So tomorrow's class is at 4:45.
Yes, sir.
Perfect. So tomorrow we meet at 4:45, and I'll start with why continuous functions are dense in LP mu. We have seen that simple functions are dense in LP mu. And by now, you have seen arguments how simple functions can be approximated by continuous functions, for example. So finally, that's what we'll have to do. That approximating simple functions by continuous functions. So tomorrow we shall start with that, and then we'll see what else can be done. Any questions today?